Hello students, in the last section we have discussed about the Poisson's equation, Laplace equation and application of Laplace equation, and also you have seen one of the example of the Laplace equation. Now in this section we consider one theorem that is known as uniqueness theorem. So why we require the uniqueness theorem? So that is consider by seeing the statement. So let us see what is the statement of uniqueness theorem. A statement of uniqueness theorem is a solution of Poisson's equation of which Laplace equation is a special case that satisfies the given boundary condition is nothing but a unique solution, right? So whatever we get the solution of Poisson's equation, if that solution, or it might be a Laplace equation which is nothing but a special case of Poisson's equation, if that satisfies the given boundary condition, then it is considered as the unique solution. So hence that is a statement of uniqueness theorem. So now this is a statement. So now let us prove this uniqueness theorem, right? So for proving the uniqueness theorem, now what we do is let us assume that we have a two solutions. So we consider a Laplace equation for this, right, which is a special case of Poisson's equation. So let us assume we have a two solutions. One is v1 and one is v2. For v1 and v2, both general function of a coordinate use. Therefore del square v1 is equal to 0 and del square v2 is equal to 0. This is equal to 0. So these are the two solutions where we have obtained from the Laplace equation. So to prove this uniqueness theorem, so let us first consider these two equations or these two solutions of Laplace equation. Now next what we do is we assume that both v1 and v2 satisfies the boundary conditions, because to prove the uniqueness theorem, so we have to assume that both v1 and v2 satisfies the boundary conditions. So now let us define a new difference potential, that is v1 minus v2 is equal to vd, right? So now whatever we have got the equation previously, that is v1 minus v2. So to achieve this in the Laplace, so what we consider is we consider as del square vd is equal to 0. That is nothing but del square v1 minus v2 is equal to 0, right? So if you consider the difference in potential, because we have to satisfy the both, and now we have to make v1 and v2 is equal to same, then only it satisfies the uniqueness theorem. Now what we do is you take a vector identity, already you have seen in the previous module, that is del dot vd is nothing but equal to v into bracket del dot d plus d dot del v, right? So this is a vector identity you have seen in the previous modules. Now here what we consider is, let us take v is equal to vd, right, and d is equal to del vd, d is equal to del vd. So then we have the simplified equation, that is del dot, instead of v you should put vd, and instead of d we put a del vd. So therefore it becomes vd into bracket del square vd plus del vd square. So after substitution we'll get this equation. So now you use this equation. So but we already know that del square Vd is equal to 0. Then we have the equation, that is del dot Vd into bracket del Vd is equal to modulus of del Vd square, because del square Vd becomes 0. So this equation we got, right? Now let us consider, as it is in terms of divergence, so we consider integration over the surface or over the volume, right? So next what we do is taking the volume integral over the volume gives integration over volume del dot Vd del Vd dv is equal to integration over volume modulus of del Vd square into dv, right? So this is nothing but integration of that previous equation to get volume integral. Now consider the divergence theorem. Already you know that integration over closed surface d dot ds is equal to integration over volume del dot d into dv, right? Now you see in the right hand side of the above equation can now be written in terms of surface integral, that is surface integral. Now we can now here d becomes what? Vd del Vd. So therefore instead of d we write it as Vd del Vd dot ds, which is nothing but equal to integration over volume, that is del Vd square dv. So this final equation we have got. So now you can see in the left hand side it is a surface integral, in the right hand side it is a volume integral. Now surface integral can be evaluated by considering the surface of a very large sphere with a radius r. So you can evaluate the surface integral by considering the very large sphere of radius r. Now when r is very large, both v1 and v2 can be treated as a point charge, since the size of it will be very small compared to r, right? So hence the surface integral on LHS decreases. So as we are knowing that surface integral can be evaluated by considering a very large sphere with a radius r. As r is very large, both v1 and v2 can be treated as a point charge. Since size of it will be very small compared to r, hence surface integral of LHS decreases and approaches to 0, right? So therefore hence we get only the right hand side equation, that integration of over volume, that is modulus of del Vd square dv is equal to 0. So since modulus of del Vd square is always positive, because modulus means it is always positive, so everywhere above the equation is satisfied only if del Vd is 0, and if the gradient of Vd, that is v1 minus v2, is everywhere 0, then v1 minus v2 cannot change with any coordinates, that is it has the same value at all the point on the boundary surface. So that is what, if del Vd is equal to 0 everywhere, then the gradient is also 0 everywhere. So v1 minus v2 cannot change at any coordinates, so it will remain same for all the boundary conditions. So therefore v1 is equal to v2 gives the two identical solution, there is nothing but unique solution. So hence this is the proof for uniqueness theorem, that is which is giving only unique solution. Thank you.